Good day, everyone. It's an honor to present at the 7th International Research Conference on Multidisciplinary in Social Sciences and Technology. I would like to express my sincere gratitude to the organizers. My name is Kirubhashni Loganathan, and I'm a PhD candidate at University of Malaya. Today, I'm excited to present my work titled Solid Gel Growth of Zinc Oxide Particles on Graphene Sheets for Mode Locking in Thulium Holmium-doped Fiber Laser. Starting with the introduction, the use of fiber laser has gradually surpassed those of bulk lasers in the field of solid-state laser technology, fast reaching all fields of industrial, medicinal, and directed energy application. This huge percentage of business was generated as a direct result of the fact that fiber lasers have several advantages to offer in comparison to bulk lasers, which are bulkier, more expensive, and require more frequent maintenance. On the other hand, a fiber laser with an output power that is equivalent can be manufactured into smaller size. This is possible due to the fact that the optical fiber can be bent and folded into a smaller space. It is also possible to have a fiber that is several kilometers long in order to achieve a high gain of pumping light in a fiber laser, since the gain medium in a fiber laser is flexible and very fine in size. In addition, because optical fiber has a huge surface area in relation to its volume, the heat that is generated by fiber lasers may be effectively removed from the system. Because of this, a complex cooling system is not required for the fiber laser in order for it to operate at kilowatt level. This ultra-fast laser can be used in a wide range of applications, including ultra-precision manufacturing, non-linear optical and medical diagnostic, astronomical detection, as well as accuracy analysis and main scientific research for the reason of their very short pulse period and large peak power output. Material processing, telecommunication, spectroscopy, medicine, and directed energy weaponry are some of other applications of fiber laser. Such kind of laser radiation can be obtained by either Q switching or mode locking technology, which can be classified into active and passive operation mode. This so-called active approach has a few constraints. To begin, it is bulky and costly. In addition, an electro or acousto-optic modulator is required as an external device in order to sync the pulse, which results in the timing jitter effect that is immediately evident, particularly in the mode lock regime. As a result, the implementation of a method of pulse production that is more practical has been developed. This passive generation of optical pulses is the method that is recommended because of their small size, low cost, simplicity, design flexibility, and broad gain bandwidth. Moving on to the problem statement. Passive mode locking operation is usually driven using a semiconductor saturable absorber mirror, SSAM. The SSAM's high level of stability makes it an excellent choice for SA. The disadvantages of SSAMs are it has a long recovery time, which is in the picosecond level. It has an ultra-narrow working wavelength range, low damage ratio, complicated synthesization method, and high cost. Metal oxides have created interest in many optoelectronic device manufacturers due to their wide range of outstanding properties that can be easily changed to suit the device need. Zinc oxide has gained much interest as a potential electrode material for electronic device because it is inexpensive, has a low environmental impact, and has a high electrochemical activity. In addition, zinc oxide is an important inorganic material and the ideal choice for various electrical devices such as sensors, diodes, and LEDs. Moving on to the methodology, synthesis and characterization of graphene zinc oxide. First, zinc acetate was dissolved in distilled water and stirred well with a stirrer for 1 hour. In a separate beaker, 0.7 gram of oxalic acid was dissolved in distilled water and stirred for 30 minutes. After that, the oxalic acid solution was gradually added to the solution of zinc acetate while the mixture was continuously stirred. And in another beaker containing isopropanol, IPA, graphene was dissolved. The previously prepared solution was mixed with the graphene solution and the combination was stirred continuously for 3 hours. The solution was then centrifuged and heated at 87 degrees Celsius for 5 hours. The gel-like solution was heated in an electric furnace at 600 degrees Celsius for 2 hours in the final step. As a result, grayish graphene zinc oxide nanocomposite were formed. Moving on to the characterization of graphene zinc oxide. A high-resolution transmission electron microscope, HRTEM, was used to look into the surface structure of the sample. The zinc oxide, graphene, and the composite solution with reduced concentration were drop-casted onto the copper grade for HRTEM analysis, and the obtained results are depicted in Figure 1. Figure 1 shows that the graphene sheets are transparent and have an average lateral dimension of about 3.5 micrometer. It is clear from figure 1b that the synthesized zinc oxide powder has a particle-like structure with an average particle size of 80 nanometers. Figure 1c illustrates that the composite comprises zinc oxide particle and intercalated graphene sheets in which the zinc oxide particles are not uniformly distributed over graphene surface. And figure 1d displays that the HRTM images of the composite observed at a high magnification where the lattice has appeared with the lattice spacing of about 0.25 nanometer, which is associated with the plane of zinc oxide. The sample was then examined in detail using the energy dispersive X-ray EDX spectroscopy to get the substance composition in terms of composition element. As shown in figure 2, the elements carbon, oxide, and zinc were present in the ratio of 59.51%, 33.59%, and 6.9% respectively. The high carbon atomic percentage can be attributed to the sample being analyzed and the grid material, which is also made of carbon. It was used to increase the conductivity of non-conductive sample. The factor that no other element peak were found in the material is evident that the sample is pure. The sample were also tested using a UVV spectrometer scanned within the wavelength range of 200 to 800 nanometer. Figure 3a shows the UVV spectrum of zinc oxide where a sharp absorption peak appeared at the wavelength of 374 nanometer, consistent with the absorption spectrum of zinc oxide. As shown in figure 3b, one sharp peak and one broad peak are present in the UVV spectrum at the wavelength of 258 nanometer and 364 nanometer, respectively. The absorption peak at 258 nanometer responds to the typical characteristic peak of graphene and is referred to as an aromatic carbon-carbon bond. The absorption peak at 364 nanometer is associated with the absorption peak of zinc oxide, thus confirming the presence of zinc oxide in the composite. Moving on to the arc-shaped fiber-based SA, the fabrication process. The polishing technique was used to obtain the side polished fiber from a single mode fiber, SMF28. The polishing wheel has a sandpaper covering its entire body and is driven by a 6-volt direct current power supply. The polishing wheel then begins to rotate until a loss of 3 dB is achieved. The constructed side polished fiber is placed with the polished face facing upward on a clear glass slide. The prepared black solution is then used to coat the surface of the side polished fiber using the drop casting process. Then the fiber will be left to dry at the room temperature of 10 minutes. Moving on to the characterization of the arc-shaped fiber-based SA, twin detection method is used as a laser source generated a Mortlock pulse with a repetition rate of 18.7 MHz, pulse speed of 1.02 picosecond, and a center wavelength of 1.9 micrometer. First, the signal was transmitted along the bare SMF and later connected to the SAs. The readings were recorded. The experimental data obtained were fitted using the saturation model equation as follows. The modulation depth as zinc oxide and graphene zinc oxide were 12.31% and 14.11% respectively based on the fitted graph. Figure 6 shows the schematic representation of the Thulium Holmium-doped fiber laser cavity used. Moving on to the results and discussion. Figure 7 shows the mode locking characteristics of Thulium Holmium-doped fiber laser using graphene zinc oxide as a saturable absorber. Figure 7a shows the optical spectrum recorded from the optical spectrum analyzer. It has a center wavelength of 1895.11 nanometer and a 3 dB bandwidth of 2.26 nanometer. Figure 7b shows oscilloscope trace with a repetition rate of 11.82 MHz. Figure C shows the autocorrelator trace together with a sec square fitting curve with a pulse width of 1.7 picosecond. And figure D shows the radio frequency spectrum recording 58.2 dB as a signal to noise ratio SNR. Figure 8 shows the output power as a function of pump power ranging from 274.3 milliwatt to 449.9 milliwatt. It has an efficiency of 0.74% with a fundamental mode locking. Figure 9a shows the output spectrum within the first 6 hours of operation, and B shows the analysis of wavelength drift in the 6 hours of operation. From this figure 9, we can say that the Motlop produced were extremely stable. Moving on to the last part, the conclusion. The graphene zinc oxide have been successfully synthesized using the solder techniques. The EDX and UV-Vis analysis confirm the formation of the composite. The graphene zinc oxide base SA exhibits a modulation depth of 14.11% and a saturation intensity of 4.23 milliwatt per centimeter square. Modlock pulses were produced at a center wavelength of 1895.11 nanometer, fundamental frequency of 11.82 megahertz, and a pulse duration of 1.7 picosecond. The Modlock pulses were stable, giving a signal-to-noise ratio of 58.2 dB. The proposed fiber laser system with graphene zinc oxide-based assay has an excellent potential for application as a source of cost-effective light in the eye-safe region of 2 micron. That's all from me. Thank you.